So here's an example of a online calculator that'll sort of do it for you. Now this is a 5 milliamp motion, very sensitive. If I want to measure, let's just say 500 milliamps on it, just have to find an appropriate shunt value. You know, you obviously shunt the excess current through the shunt resistor, and you only want the leftover current that's going to flow through the motion here. Just to make it easy, I'll probably do 50 milliamps. Don't see much point in 500. Simple way to figure that out is, like I say, I've got a supply that I can vary the output voltage a milliamp at a time, so I can basically precisely put that 5 milliamps through a load, basically bring that needle all the way to full deflection. Once it's there, I can read the voltage across it, and in this case it was 0.0747. So with that voltage, with 5 milliamps going through it, let's just say, so you take that voltage divided by that 5 milliamps through Ohm's law, gives you about 14.94. Let's just say that's 15 ohms. Then you say, well, let's take that voltage, divide that by the current that we want to shunt out. So at 50 milliamps, full deflection, I just want 5 milliamps to actually go through the motion, because that's really the max current that you wanted to see. So that leaves us with 45 milliamps, and it comes up to about 1.66 ohms. So that's the value of the shunt that I would need across this ammeter for a full scale deflection at 5 right there to actually be 50 milliamps. It's basically what I have to do. I have to fine tune a resistor at exactly that value, and then basically through series of switches can shunt over to 50 milliamps or 5 milliamps. Voltage source negative to the negative of the capacitor. Positive is going through the ammeter to the positive labeled pin terminal, and then the negative labeled terminal is going out to the positive of the charging capacitor. Then you've just got these two, however many you want, switchable shunts across the ammeter. So it's really simple. Another thing to keep in mind when you're having to do these real precise resistance measurements to make a real precise resistor is obviously the lead length. So it's a pretty accurate meter, being an oscilloscope. So I've got the probes just clamped together. You can see they're letting it sit there for a little while. Got about 0.1 ohms. I grabbed some ceramic resistors from boards, just kind of pulled them off, and I happened to put enough in series to where I got pretty close to the shunt value I needed. It's just kind of cool to see how that works out. So that was about accurate. Now that I've got this guy kind of wired up, I can actually do a capacitor reform, or at least sort of try to get an idea at the lower voltages what's kind of going on there. So again, this is the main circuit. This is going to be the high voltage supply. It's going to charge this capacitor at a variable voltage that I'm going to set at a constant. Then I've got this ammeter in line, and then I've got this meter right here. It's going to show me the voltage on the cap at all times. I've got these two shunts here on this ammeter, which are going to help me read the leakage. This first one here, it's more or less bypassing the motion on here. With it on, that's how I can actually push, significant current into whatever my output is. So I really don't want to have that disengaged if I'm going to push more than 5 milliamps or so, right? The other one is switched to the shunt that I calculated for about 50 milliamps. So as long as this switch is on like that, number 5 is going to mean 50 milliamps or so. Turn it off, it's going to go back to 5 milliamps. So it's just a 10x switch basically. I want to make sure that that switch is on. I'm going to cut the circuit on. The voltage is going to be something like 60 volts, something like that. Coincidentally, it's going to be like 57 probably. So then I'm just going to turn my output on with this switch. You see the voltage go up, and you can actually see I'm still registering that small amount of current even with this basically dead short across it, because obviously that wire I'm using still presents some type of resistance. Now that I've put the charge in that capacitor, it's going to basically just sit there at about 57.13 something like that, 0.12. Now I can disengage this main shunt. What I'm reading now is on the 50 milliamp scale. So if I go to the 5 milliamp scale, again, it's very low. It's well under a milliamp, so we're in the microamp leakage there. So I'm going to cut that off because now I want to fine tune the voltage ramping up. So I'm going to slowly ramp that voltage up. And you can see as I do that on the 50 milliamp scale, it's going up about 10 milliamps. So it's going up over 10 milliamps or so, just raising that voltage up, maybe like a volt at a time. So if I kind of just like smoothly keep turning it up, and so the faster I swing it up, you can see it starts going up to about the 50 milliamp region. So let's just say I'm going to bring it up to 100 volts, right? So let me leave it about right there. You can see what that's doing. It's kind of bouncing around. So I'm going to switch it back to the 5 milliamp scale. So now you can see what that thing's doing. It's putting in at 100.72 volts. This is kind of like the action that you see with reforming. However, it's staying fairly low, under half a milliamp or so. But, just kind of seeing that wonky action going on, it's interesting. Right. So I would say since it's not really jumping up too high, then I can keep going higher. So go back to the 50 milliamp scale. Now let me bring it up to like I'm going fairly slow. If I want to go faster than this, then I need to engage that main shunt again. All right. So you just have to keep the switches in mind. If you forget, then you're probably going to burn that thing out. So let me see. Let me put it right there. So I'm trying to find a point where I can sort of see like a good dancing. 135.8 or so. So now we're getting the swing up to, saw one at about a milliamp or so. Still not bad. Alright, so I'm just going to keep going up here. I'm going to go up to, really kicked up. Really starting to kick up now. Yeah, so let me leave it at that 147.4. So again, you kind of see what that thing's doing. I mean, you get the idea of some kind of activities going on, right? So anyway, if sit there and let it do that for long enough, at that voltage, then should eventually over time sort of settle down, which it looks like it's sort of doing now, right? It's still gonna ever so slightly probably show the tiniest fluctuation there. Alright, so I just took it to about 200 now or so, 202, and we can see it's got sort of more of a steady leakage, but it's somewhere around the it's a quarter of a milliamp, about 250 microamps. So I don't know. Again, that might be something you have to refer to the spec sheet. This is technically sort of a visually bad capacitor. So about 260 or so. Now we can see over a milliamp. So this is a prime example. What you're looking for over time is to see that go down. Took a while at like the 150, 170 volt region for that dancing to sort of settle. It's hard to say if it's really going to settle over time at this point, but yeah, I just kind of want to see it maybe keep going down like that. And the battery voltage, you know, coming down now. So been sitting here doing this for a while. It's dropped a couple 100 millivolts. So I'd like to see that go down to less than half a milliamp. I'm not sure if it will, but I suppose it will eventually. Right, so it kind of looks like it wants to make its way down there. Maybe kind of hold out on I don't know, 400 or 500 microamp leakage, which seems like a lot, but I don't know. That might be not too bad for such a big capacitor like that. Yeah. So again, I really don't want to sit here forever and do this, but that's pretty much the idea right there, right? Like you get the idea. I would basically do the same thing here up to about 400 volts on a particular capacitor like that. Just sort of observing what's going on. So without really knowing anything about the specs, you see now it's under half a milliamp, so that's good. Without really knowing anything, if that thing was to just kind of keep dancing for a really long time, you know, up in like the 2 milliamp region, something like that, then I would think, all right, that's pretty suspect. You know, I'm only at 260, and it's doing that. It's not settling down. Something's probably wrong with that capacitor, right? But again, I'm sort of kind of using these. I plan on using them for a particular bootleg Tesla coil purpose. So far, it's kind of looking like it might be all right. So, drain that guy down because I don't need to really test it any further. A good thing to do would be to put that shunt on like that, right? So you don't get that reverse current, I guess you could say, trying to burn that guy out. Shouldn't have done that, I totally forgot, but yeah. Cut it back on real quick, just to test. Okay, yeah, we're still good, we're still good. Take that guy off. And yeah, again, so at about 57 volts or so, see that leakage is like pretty much nothing. And start bringing the voltage back up again. Yeah, so with these lower voltages, it's very easy on the cap, like bringing up the voltage and whatnot. Start pegging it once I get up to about this point. And yeah, like 78 volts, something like that. Still, leakage isn't bad, but now I start creeping up into the 100 microamp region. So yeah, it's pretty cool.